these are the notes for learning target 3.4, which says I can solve problems using unbalanced forces, or the F net is equal to mass times acceleration, which is another way to say that the forces are not balanced. So if forces are unbalanced, an object will speed up, slow down, or change direction. Consider horizontal and vertical forces separately. So real quick, here's an example of an object where the forces are not balanced. And so under it, on your notes, you can label that unbalanced forces end up in a change in velocity. Objects with larger net force or more unbalanced force will experience larger accelerations. So here we've got a small net force, which will result in a small acceleration. You can put that on your notes because this force is just a little bit bigger than that force, whereas a large net force, meaning a big difference in forces going in opposite directions, causes a large acceleration. So you can add these labels to your diagrams on your notes. Objects with larger masses will experience smaller accelerations given the same net force. So here you can see that the net force acting on this cart is the same as the net force acting on that cart, that these forces are the same amount larger than the friction forces. But since this cart has a smaller mass, then it has a larger acceleration. Whereas this cart, because it's so full, it has a larger mass and therefore a smaller acceleration. And so the equation that reflects those patterns that we see with acceleration and mass and net force is this equation, which says that the net force is equal to the mass of the system multiplied by the acceleration of the system. And the net force is going to be in the same direction as the acceleration. So for example, in our pictures of our shopping carts, because there's more force to the right than to the left, the shopping cart is going to accelerate to the right. For example, number 1, we have a shopper that is pushing a 20 kilogram cart using 40 newtons of force, and we have to determine the acceleration of the cart if there's no friction. So here is the force diagram that I would draw for our situation. And we can see that the normal force pushing up on the cart from the ground must be equal to the gravitational force pulling down on the cart from the earth, because the cart is not going to change velocity upwards or downwards. It's going to stay at the same height the entire time that the person's pushing it. But if we look at the x direction, because those are both in the y direction, if we look in the x direction, we see that there's a force provided by the person pushing to the right, but there's no force counteracting it. And so here we have unbalanced forces. The strength of that force that they're applying is 40 newtons. And so what this statement says is the net force in the x direction is going to be equal to how hard they're pushing, how hard the person is pushing. And that force is going to be equal to the mass of the cart times its acceleration. So here we have 40 newtons, which is the amount of force that they apply, equals 20 kilograms times acceleration. And if we divide both sides by 20, we get that the cart is going to accelerate 2 meters per second squared to the right, because it's in the same direction as the unbalanced force provided by the person pushing. For the second example, we have a crane lifting a 300 kilogram container off the ground and causing it to accelerate at 1.2 meters per second upward. Determine the tension force provided by the crane. And so first we need to make a force diagram for this container. And here we've got a larger tension force than we do a gravitational force, because we know that the container is accelerating upwards. So if it's accelerating upwards, then it must have a stronger force upwards than downwards. We'll show that with our congruency markers as well. And now we've got the F net is equal to the mass times acceleration. And so we can figure out, because the container has a mass of 300 and it's accelerating at 1.2 meters per second squared, then its net force is going to be 360 newtons upward. Now, net force is not a force on our force diagram. What the net force means is that however big this force is, it must be 360 newtons larger than this force, because the forces are unbalanced, and the net force tells us how unbalanced are they? Like, what is the difference between those forces? So in order to figure out these two forces, we need to figure out one of them by itself. And since we don't have any equation to solve for tension force, we're going to calculate what the gravitational force is. The gravitational force can be found by multiplying the mass times the acceleration due to gravity. In this case, 300 kilograms times 9.8 meters per second squared. And we get that the gravitational force is 2,940 newtons downward, which we can add to our force diagram. Now that we know the gravitational force pulling down on the container, we can say that this tension force has to be 360 larger. So another way to write that is that the net force, or the difference, is going to be equal to the larger force, or the tension force, minus the smaller force, or the gravitational force. If we substitute the values we already know in, 360 and 2,940, we can then add 2,940 to both sides and get that the tension force is equal to 3,300 newtons upwards. And so our answer would be 3,300 newtons upwards is how much tension is provided by the crane. Thank you for watching these notes.